Welcome to this next video in the playlist on vector spaces. In this video, what we're going to introduce is the concept of a basis of a vector space. Plural is bases, okay? What I'm firstly going to do then is just give you the usual setup, okay? So I'll draw my normal picture of a vector space, and then we'll go straight in for the definition of a basis. Okay, right, so let's start with the setup then. So once again, we'll be working with an arbitrary vector space, capital V, which is over some field, capital F, okay? And I will draw my usual picture of a vector space over the field, capital F. Remember, a vector space fundamentally is just a set of symbols which we call the vectors. Okay, so I'll draw my set of symbols like so. So here is my box, which will be my set, which is going to contain my vectors, and I'll colour it in purple here. So this is my set of symbols, which is going to form the vector space. And then to actually turn this set of symbols into an interesting algebraic structure, what we do is we define two composition laws on it. Okay, the first is called addition, and this is a composition law of vectors with vectors. Okay, so I can add any two vectors from the vector space together using this composition table. So this is a great big table which tells me what one vector added to another vector is actually going to be equal to, and this addition composition table here obeys the axioms of the abelian group. Okay, then we have a second composition law. Okay, so I'll draw a second composition table here, which is called scalar multiplication. Okay, and I'll colour scalar multiplication's composition table in red here. And this isn't a composition table where we can compose elements of the vector space with elements of the vector space. Instead, it's a composition table involving elements of the field being composed with elements of the vector space. So we can scalar multiply all elements of the vector space by elements of the field. So what we can do is we can give all the elements of this field, capital F, a row in this scalar multiplication composition table, like so, and we'll give all of the vectors in the vector space a column in the scalar multiplication composition table. And then if you want to know what some element of the field scalar multiplied with some vector in the vector space is, you just take the row corresponding to that element of the field, like so. You take the column corresponding to the vector that you're interested in, and then this box here, this entry in the scalar multiplication composition table, this will give you the answer as to what that vector scalar multiplied by that element of the field is actually defined to be equal to in your vector space. Okay, and this will always be some other vector back within the vector space, so it will never be outside of the vector space. Okay, right, and scalar multiplication must obey a whole bunch of axioms as well to make it actually interesting. So it must obey closure, which means that all the answers in this great big scalar multiplication composition table must be back within the vector space. It must obey associativity with multiplication in the field. It must have the identity element of the field, the multiplicative identity of the field, scalar multiplying all vectors to give that vector back again, and then finally it must obey two distributive laws as well. And if you want to hear those in more detail, do watch my video on the definition of a vector space. Okay, right, there's our picture then of what a vector space is. So we've got a nice picture of what we're actually going to be working with here. Okay, so we're now going to see what the definition of a basis of a vector space is. Okay, and as I say, the plural for a basis is bases, like so. Okay, so we're just looking at one initially, so let's have a look at what the definition of a basis is. So a basis for a vector space, capital V, over the field, capital F, is fundamentally a set of vectors. Okay? So I'll draw this here. So this basis is going to be a set of vectors, and for our purposes now we'll just have a finite set of vectors, although the principle, the concept, can be extended to infinite sets of vectors. Okay, but to keep this simple we'll just have a finite set. Okay, so here is capital B is the symbol for a basis. Okay, and it's going to be a set of vectors from our vector space. So we're going to have V1, V2, all the way along to Vn here. Okay, like so. So this is a bunch of vectors from our vector space. So all of these are in our vector space. So v1 I'll put here, v2 I'll put here, and then it'll go on and on all the way until we get up to Vn. So these are just symbols from our vector space. So I'll colour them all in orange here. Okay, so a basis is a set of vectors from our vector space. So it's a subset of our vector space. Okay, and it has two special properties. The first is that the span of these vectors in this set is equal to the entire vector space. Okay, so if you don't know what span is, see the previous video in this playlist on vector spaces entitled Linear Combinations and Span. Okay, so the first property is that the span of this set of vectors, B, is actually going to be equal to the entire vector space. Now let me just remind you of what the span of a set of vectors is actually equal to. So remember, this means take every possible linear combination of the vectors in the set, capital B, and put them all into a set. So it means absolutely everything of this form, C1v1 plus C2 v2 plus all the way up to Cn Vn, where these Ci's are elements of the field, capital F. Okay, so things of this form, vectors of this form, are called linear combinations of the vectors in the set, capital B. Okay, and to construct the span of B, what you do is you take all linear combinations of the vectors in this set and stick them into a set. Okay, so let me make absolutely clear what I mean by this. I mean C1 here can vary over every element of the field, C2 can vary over every element of the field, and all the way up to Cn can vary over every element of the field. Okay, so you take every possible combination of elements of the field that you can put in front of these n vectors here, you add them all up together and you get an answer, you stick that into the set. Okay, so you go through every possible combination, construct this thing, and then stick it into the set, collect them all together, and that is what is meant by the span of this set of vectors, capital B. Okay, and the first property that this set of vectors B must obey is that this set, if we take all linear combinations of this set of n vectors, it must equal the entire vector space. So every single vector in the vector space can be gotten by taking a linear combination of the vectors in the basis. Okay, so that's the first property that the basis must obey. The second property that it must obey, and I'll put this over here, is that it must be linearly independent. So this set, capital B, this basis set, must be a linearly independent set of vectors. Okay, now I'll just remind you of what is actually meant by a linearly independent set of vectors. Okay, so the definition then of linearly independent is that there is only one possible linear combination of those n vectors which gives the zero vector. Okay, so if we are looking at the solutions to this, C1 v1 plus C2 v2 plus all the way up to Cn Vn is equal to the zero vector in our vector space, the additive identity of our vector space, there is only one solution to this, and this is the solution where all of the scalar coefficients here have to be equal to the additive identity of the field, zero in the field, the scalar zero. Okay, so if a set of vectors is linearly independent, it means that all of the scalar coefficients have to be equal to zero in order for a linear combination to actually give you the zero vector. Okay, so there's only one linear combination of the vectors that actually gives the zero vector as its answer, and that is where all of these scalars are actually zero in the field. Okay, now, in the previous video on linear independence, in this playlist on vector spaces, we saw the consequence of this being true. We saw that one of the consequences of this being true for a set of vectors, so one of the consequences of a set of vectors being linearly independent, is that if you have two distinct linear combinations of the vectors, those two distinct linear combinations of the n vectors cannot give as their answer the same vector in the vector space. Okay, what that means is that if you go through all the possible linear combinations of these n vectors, you will get all different answers. You will never get the same answer more than once. So all the different linear combinations of these n vectors will be different vectors in the vector space. That is one of the consequences of this being true. Okay, so what do we now know then? Okay, a basis then is a set of vectors which spans the entire vector space. So every vector in the vector space can be written as a linear combination of these n vectors. Okay, so I'll stress this even more. If I have some arbitrary vector from my vector space, little v is an arbitrary vector from my vector space, I will be able to find elements of the field C1, C2, all the way up to Cn, such that v is equal to this linear combination of those vectors. So I will be able to find some linear combination of these n vectors such that this is true. Okay, so that's what condition number 1 tells us. Condition number 2 of linear independence tells us that it is unique. There is only one such linear combination of the vectors v1, v2, all the way up to vn, which gives v as the answer. Okay, so there is one and only one linear combination of these n vectors in the basis of the vector space which actually gives you the vector v. Okay, so one and only one linear combination of the vectors will give each of the vectors of the vector space. Okay, that then is what a basis actually is. So what this means then is that if you have an arbitrary vector in your vector space, capital V, you can write this vector as a linear combination of these n vectors. Okay, now there's some important nomenclature that I want to tell you about now. Okay, these scalars, these elements of the field that you have to put in front of the vectors of the basis in order to actually create a linear combination which equals this vector v, these are called the coordinates of the vector capital little v here with respect to this basis capital B. Okay, so these are called the coordinates of the vector v, so coordinates of v, and I'll put with respect to the basis capital B. Okay, so if you have different bases, you can write vectors with different coordinates basically. So the same vector in this vector space will have different coordinates relative to different bases. Okay, so if you have a basis, you can find the coordinates of any vector with respect to that basis. Okay, right. Now what you can actually even do then, the next concept, is that you can actually construct a coordinate vector for this vector little v with respect to that basis. So what you can actually do is put these elements of the field into a column or into a row, okay, like so. So we can put C1, C2, all the way down to Cn, okay, and this is called the coordinate vector of this vector little v in our abstract vector space with respect to this basis. So this is what's called the coordinate vector. So once you've got a basis, then you can write all of the vector spaces as all of the vectors in the vector space as coordinate vectors with respect to that basis. Okay, so having a basis is very, very useful because it allows you to write all of the vectors of the vector space in terms of coordinates, like so. Okay, right, so it allows you to ascribe a coordinate vector to all of the vectors of the vector space. Right, okay, now, even more, what I want to consider now is what happens if we add two vectors which have been decomposed in this way into their linear combination in terms of this basis. Okay, so if we have two vectors, let's say v and v bar, okay, we can decompose them into their coordinate vectors with respect to this basis. So I can write v as some linear combination of these n vectors, so c1, v1 plus c2, v2 plus all the way up to cn, vn, like so, and I can write v bar as some linear combination of these vectors. And remember, there's only one linear combination. I can write each of these as one and only one linear combination of the vectors v1 all the way up to vn. So c1 bar, c2 bar, v2 plus all the way up to Cn bar Vn, like so. Okay, so I have these two vectors then in my vector space written as their one and only one linear combination of these basis vectors. Okay, and now if I want to add the two of them together, so if I want to add v to v bar, let's think about how you would do that in terms of the coordinates. Well, of course, adding this to this just means adding these two huge linear combinations to one another. So we are just adding these two things together. Okay, but we've looked at expressions like this in previous videos in this playlist, and we know how we can handle them, but I'll go over it quickly now. Okay, so if we want to add this linear combination to this linear combination, okay, what we can firstly acknowledge is that addition obeys beautiful properties. It obeys the beautiful property of associativity and commutativity. Okay, those two incredible properties. Okay, and what associativity and commutativity mean is that we don't need to worry about where the brackets are in addition, neither do we actually need to worry about which way round we're adding things together. Okay, so what we're going to do is view all of these things as just being vectors. So I know we've got scalars and then a vector, but the answers here are just vectors. So for now, ignore the fact that we have some scalar multiplied by some vector. Just treat all of these things that I'm underlining in red as vectors, and I'm just adding 2n lots of vectors together. Now, because of addition obeying associativity and commutativity, I can just move these around freely, basically, okay? It really does not matter. We don't have to worry about where the brackets are, neither do we have to worry about which way round things are. Okay, so what I can do is just rearrange this beautifully. So what I want to do is get the terms which have the same vector, same basis vector in, nearby one another. So I'll have, this is going to be equal to C1 V1, so I keep this one up here. Then I'm going to move this one close to it, so I'll have plus C1 bar V1, okay, and then I'll have plus the C2 V2 from over here, and then I'll have this one close to it, plus C2 bar V2, and then we'll continue on, so plus dot dot dot, all the way up to Cn Vn plus Cn bar Vn. Now, why have I rearranged it like that? Well, it's because now what I can do is factorize out the basis vectors, basically. So if I've got an expression like this, what I can do is turn this into something that looks like this. So I can have C1 plus C1 bar times V1, like so. Okay, so understand how extraordinary that is, because this is an addition in the vector space. We're adding together these two vectors, whereas this is addition in the field. I'm adding C1 and C1 bar together in the field. Okay, and I can continue this up. So we'll get C1 plus C1 bar times V1 plus C2 plus C2 bar times V2 plus, and it will go on all the way up to Cn plus Cn bar times Vn, like so. Okay, so I've now re-expressed that like so. Okay, and what I've now got is the answer here written in terms of my basis. Here is a linear combination of my basis vectors, and this is the answer to v plus v bar here. Okay, written beautifully already in terms of a linear combination of the basis vectors. Okay, so what would its coordinate vector be? Its coordinate vector would be c1 plus c1 bar, c2 plus c2 bar, all the way down to Cn plus Cn bar. Okay, and hopefully you appreciate how beautiful this is now, that if we have a basis, we can write all of the vectors in terms of coordinate vectors with respect to that basis, and then the way we add vectors together is we just add the coordinates like so, because you can hopefully appreciate that the coordinate vector of this first vector v is just c1, c2 all the way down to cn, and the coordinate vector of our second vector v bar is just c1 bar, c2 bar all the way down to cn bar. So I've just literally added their coordinates together. Okay, in addition, this gets better because if we consider what scalar multiplication is in terms of the coordinate vectors, okay, so let's consider taking the vector v, okay, and scalar multiplying it by some scalar in the field, c, okay, so now let's consider c times v, so we're considering c times the linear combination here, so I'll write v out as the linear combination in terms of the basis vectors, so we've got c1 v1 here, c2 v2, plus, and it will go all the way on until we have Cn times Vn here, okay, like so. And now what we can do is we can expand this side. So remember, we're trying to do the same thing. This is the answer to what c times v is equal to. We're trying now to re-express this as a linear combination of our basis vectors so that we can write it as a coordinate vector. Okay, right. So now what we can do is apply distributivity, so we can say that c is going to distribute over the addition of these vectors here. Okay, so we can split this down into c times c1 v1 plus c times c2 v2. As I say, we've used this sort of manipulation many times before in previous videos. C times cn vn. Okay, like so. Then what we can do is apply associativity of scalar multiplication with field multiplication to say that when we've got something of this form, c times c1 times v1, we can rewrite that like so. C times c1, where this is multiplication in the field, and then the answer scalar multiplied by v1. So we'll do that for all of these, and then we'll get that the answer here is c times c1, where this is multiplication in the field, scalar multiplied by v1, plus c times c2, where this is multiplication in the field, scalar multiplied by v2, and it will continue on all the way up until c times cn, scalar multiplied by vn. Okay, so here then is the answer to what c times v is, written beautifully as a linear combination of my basis vectors v1, v2, all the way up to vn. Okay, so you can see then that the coordinate vector of c times v is just c times c1, c times c2, all the way down to c times cn, like so. So scalar multiplication in terms of coordinate vectors is absolutely beautiful. If you have a vector written in terms of its coordinate vector with respect to a basis, and you want to scalar multiply it by an element of the field c, all you do is multiply in the field all of the coordinates in the coordinate vector by that element of the field c. Okay, so this is why having a basis is so useful, because what we can use it to do is describe all of the vectors in the vector spaces as coordinate vectors with respect to that basis, and then addition is beautiful and scalar multiplication is absolutely beautiful. Okay, right, so we'll call it there for this video, and in the next video what we'll do is start discussing some examples of bases of vector spaces.